Hello everyone, myself Dr. Ramgopal, working as Associate Professor in Mathematics in the Department of Humanities and Sciences, MLR Institute of Technology, Hyderabad. I welcome you all to today's session on poles and residues. So here, today I am going to discuss about the singularities, the different types of singularities, then poles, residues and few examples. Now we know that the functions which are analytic in a given region. We have dealt with functions which are analytic in a given region, but there are many functions which are not analytic at a particular point. For example, z equal to a. So there are several functions which are not analytic at certain points or in the domain. So those points are called singularities of the function. So if the function is not analytic at this point z equal to a, that means a point at which the function ceases to be the point at which the function ceases to be analytic is called a singular point. That means fails to have a derivative at that point. Now a pole is a particular type of that singular point. So simply we can say pole and singular points are the same, but there is a small definition is there that differs pole from a singular point, but both are similar. Now residue at a pole is a complex number that characterizes the singularity of the function at that pole. So that characterizes the singularity of the function, and residue represents the contribution of the pole to the integral of the given function. So residue represents the contribution of the pole to the integral. So that means to evaluate, in some cases, to evaluate the integral, we use this concept of finding residues that we will discuss in the next in coming sessions also. Now coming to the first one, zeros of an analytic function. For example, some f of z is given. Now to find the zeros of that function, equate that f of z to 0 and find the values of z. For example, f of z is z minus 2 by z minus 3. Now if you equate this to 0, this goes to right hand side. So only numerator is 0, z equal to 2. So zeros can be obtained by equating the numerator to 0. So a 0 of an analytic function is a value of z such that f of z is 0. And a point a is said to be 0 of analytic function if f of a equal to 0. So to find the zeros of the given function, equate the numerator to 0 simply. Zeros of mth order. For example, if that value is repeated m times, so sometimes we may write the given function as z minus a power m into some function of z, some g of z for example. Then by equating f of z to 0, we will get z equal to a is a repeated value that repeats m times. So this z equal to a is called a 0 of order m. Singular point, a point at which the function ceases to be analytic, that means fails to have derivative, that is called a singular point. And isolated singular point, here the function f of z is not analytic at the point z equal to a, but it is analytic at each and every point in the neighborhood of that z equal to a. For example, this is the point z equal to a. The function is not analytic at this point, but it is analytic at each and every value of that neighborhood. Then the point is z equal to a is called isolated singularity. Now coming to the poles of an analytic function. Just now we have discussed a pole is also similar to a singular point. Pole is a certain type of singular point. If z equal to a is an isolated singular point of an analytic function, then this function can be expressed in Lorentz series as f of z equal to sigma a n z minus a power n plus sigma b n by z minus. Here z minus a that has positive powers here, and here the negative powers, z minus a power n. It comes to numerator, then it becomes minus n. So this second part, this is called the principal part of the series, the principal part of Lorentz series. If this principal part has finite number of elements, finite number of terms, that means For example, this Bn will be 0 for n greater than m. So there are only m terms. If n is greater than m, then Bn will vanish. Bn is 0. So if this principal part contains a finite number of terms, say m, that is Bn is 0 for all n greater than m, then the singular point z equal to a is called, the pole of order m. Pole of order m. So in other words, if all the negative powers of z minus a after nth term are missing, that means vanish, then z equal to a is called a pole of order m. Simply, if this principal part has finite number of terms, so Bn is 0 for some n greater than m, so there exists m terms only, which is a finite number. Now pole of order n. So here, if there exists a positive integer n such that limit z tends to a, z minus a power n into some f of z, this some value exists, a finite value, then z equal to a is called a pole of order n. Simply here z minus a equal to 0, z equal to a is a pole and it has the power n. So then it is a pole of order n. Simple pole. A pole of order 1 is called a simple pole. For example, f of z is z by z minus 2. Then by equating the numerator to 0, we can find zeros of the function. By equating the denominator to 0, we can find the poles of the function. So here z equal to 2 is a pole, and what is the power here? 1. So it is not a non-repeated one. So z equal to 2 appears one time only. So it is a pole of order 1. For example, here we have some z minus 2 whole cube. Then z equal to 2 comma 2 comma 2. Then this 2 is a pole of order 3. So previously z minus a power n. So the same thing here. Now coming to the next definition, essential singularity. If the principal part contains infinite number of terms, then the point z equal to a is called essential singularity. So if it has finite number of terms, then it is called a pole. Infinite number of terms, essential singularity, and removable singularity. If the principal part contains no terms, there is no term in the principal part, then z equal to a is called removable singularity of f of z. So essential singularity means if the principal part contains infinitely many values, and if there are no values, then z equal to a is having removable singularity of the function f of z. So these are the definitions that we need to know to evaluate the line integral of the given function. So here we can use the concept of poles and residues to evaluate the given function that will be discussed in the coming sessions. Now coming to the next one, residues. The quotient of 1 by z minus a. The quotient of 1 by z minus a. Here some quotient q1 for example. So this is called the residue of the function f of z at z equal to a. But from where we need to consider this quotient? From the Lorentz series expansion. So the quotient of 1 by z minus a in the Lorentz series expansion of f of z about the singular point z equal to a is called the residue of f at that point. Simply to find the residue at a pole z equal to a, first find the Lorentz series expansion, simplify it, then consider the quotient of this 1 by z minus a. So this is called the residue of f at z equal to a is q1. So it is we can denote it by the notation residue of f at z naught, or else simply residue of f of z at z equal to z naught. And here, so the quotient of 1 by z minus a in Lorentz series is b1, and using that formula b1 is 1 by 2 pi I line integral f of z dz. So here we can find this line integral using this residue. So line integral c f of z dz is 2 pi I into b1. What is b1? Residue at z equal to a. So if you have the residue of the function at z equal to a, you can evaluate this line integral. That is the main advantage of finding residues. Now the next one is calculation of residues. How to find the residue or at a pole z equal to a? There are two ways. One is using Lorentz series expansion, and the second one is the formula, using the formula to find residue. So first identify the pole z equal to a be a pole. Let z equal to a be a pole. Then residue of f at z equal to a can be obtained in two different ways. You can find the Lorentz series expansion or else you can use the formula. So Lorentz series expansion or else the formula to find residue at a pole. Now how to use the Lorentz series expansion? Simply expand the given function in as Lorentz series and then consider the quotient of 1 by z minus a, which is the residue of f at z equal to a. That is one of the procedures. Second one is using the formula. Here residue, for example, if z equal to z naught is a simple pole means repeated only one time, means it's a non-repeated one. So if z equal to z naught is a simple pole, then the residue at that pole can be calculated using this formula. Limit z tends to z naught, z minus z naught into f of z. So limit f of z multiplied by z minus z naught. This z minus z naught will be in this f of z in the numerator. Those two will be gets cancelled. So limit z tends to z naught, z minus z naught into f of z. This gives the residue of f at z equal to z naught. For example, if the function f of z is in this form, some phi of z by some omega of z, in which the denominator is can be 0 but numerator cannot be 0, because if the denominator is 0 we can find the poles, the singular points, particularly the poles. Then the residue of f at z equal to z naught is the ratio of phi at z naught by psi dash at z naught, provided this psi dash z naught is not equal to 0 or omega dash z naught is not equal to 0. So we can use this formula when the function f of z is in this form type. For example, f of z is cos z, then I can write it as cos z by sin z. So you can find the poles of this function sin z equal to 0. So z equal to plus or minus n pi, 0 and n pi, and where n is 0, 1, 2 and so on. So the denominator can be 0 but the numerator cannot be 0, and the residue at, for example, at 0 can be calculated using this formula phi of z by psi dash at z naught. And residue at a pole of order m. So for example, we have f of z is something like z minus a power m. That means z equal to a is a pole of order m. Then the residue can be calculated using this formula. Limit z tends to z naught 1 by m minus 1 factorial d power m minus 1 by dz power m minus 1. So m minus 1th derivative of z minus z naught power m into f of z. For example, if you put m equal to 1 here, automatically you will get the residue at a simple pole. M equal to 1 means of order 1. A pole of order 1 is called simple pole. So if you substitute this becomes z tends to z naught 1 by 1 minus 1 and 0 factorial. So m equal to 1, there is no derivative, z minus z naught power 1 into f of z. So which is the same formula, z minus z naught into f of z. So if you know this formula, you can find the residue of a function at a pole of any order, even for a simple pole and a pole of order m also. Let us solve some problems. So find the zeros and poles of z plus 1 whole square by z square plus 1. So given f of z is z plus 1 whole square by z square plus 1. So zeros can be calculated by equating the numerator to 0. Z plus 1 whole square is 0. Z plus 1 is 0. Z equal to minus 1 2 times. Similarly, poles can be calculated or can be obtained by equating the denominator to 0. Denominator is z square plus 1 is 0. Z square is minus 1. Z is plus or minus I. Similarly, coming to the second one, find the poles. So, poles can be obtained by equating the denominator to 0. Cos z equal to 0. So, when this z becomes 0, for example, we know that 2n plus 1 pi by 2. For this, you will get, for z equal to this, cos z becomes 0. So, these are the poles. By changing the value of n, different values for n, you can get different poles. Similarly, cot z, poles of cot z, f of z is cot z. Cot z means cos z by sin z. So, by equating the denominator to 0, sin z is 0. So, sin z is 0 means sin n pi is 0. Sin n pi is always 0. So, z is plus or minus n pi, where n belongs to z, set of integers. Similarly, find the poles and residues of this function. So, f of z is 1 by z plus 1 into z plus 3. Now, here the poles can be obtained by equating the denominator to 0. So, z equal to minus 1 and z equal to minus 3. So, therefore, z equal to minus 1 comma minus 3 are the poles of order 1. Both are simple poles. Now, to find residue of f at z equal to some z naught, what is the formula? Limit z tends to z naught, z minus a into f of z. So, now residue of f at z equal to minus 1. Limit z tends to minus 1. So, that z minus a means z plus 1 into the given function. So, obviously here these two gets cancelled. Now, put z equal to minus 1. Minus 1 here. So, 1 by 2 is the answer. Similarly, residue of f at z equal to minus 3. So, limit z tends to minus 3, z plus 3 into 1 by z plus 1 into z plus 3. Now, these two gets cancelled. By applying minus 3, we will get z plus 1, z equal to minus 3, minus 3 plus 1, minus 2. So, minus 1 by 2. Like this, we can find the poles and corresponding residues also. So, in today's session, I have introduced some important definitions, different types of singularities. One of those is pole and then residue. So, if there are n poles, we can find n residues. And to find the residue, we can use either the Lorentz series expansion or else the standard formula. Using the standard formula, we can find the residue of a pole of any order. So, in the next session, we are going to solve some more problems on the same topic, poles and residues. So, this is for today's session. We will meet in the next session. Thank you very much.